Let's start at 16. Hello all. Today is the third weekly session. I'll introduce myself again. I'm Jagriti Patil, TA for the course of Biomedical Signal Processing that's taken by Professor Sudipta Mukhopadhyay. This is the live session for the lectures from 12 to 17, whose assignment is due tomorrow. I'll just give a brief summary of what all lectures, like what the content was there in the lectures. But before starting that, I'd like to ask you that how was it through the first week, the second week, or is there something you guys want me to improve or add some more questions to the assignments, or it's like whatever you feel, you can just tell me, or I don't think so that you have an option of chat over there, but you can unmute yourself and speak. I can note it down so that I can improve it from the next session onwards. Is there anything? Okay, someone gave a thumbs up saying, okay, I suppose that it's fine. Okay, so we'll start for today's session. Same as usual, we'll review the lecture from 12 to 17, and then in the end, we'll have 10 questions from the previous year's assignment, which will help you to solve the coming assignment that's due tomorrow. It's more of theoretical, so this week you'll just only study that what are the different types of filters and all. At the end of this course or module, you'll learn, okay, how to implement them. So there are some tutorials and coding next to it. So as in when we progress through the course, as it's a 12-week course, so be patient and you'll be able to learn all these things eventually. So let's gather some motivation that why were like some of you can unmute yourself and say that why are we actually learning this, what's the main motivation behind doing this biomedical signal processing, or why are you all interested, not as the first session, but that is like till now what you learned and how you can use it, or is it something that is useful for your, say if someone's doing bachelor, someone's doing masters, because we have plenty of time, let's use it. Yeah, yes, go ahead.
Uh, Hello, ma'am. Uh, so good evening. I actually started this course because I'm an undergraduate in biomedical engineering, and one of the subjects for this course was biomedical signal processing. But like I joined this course for curiosity, but in comparison to that course and the content in this course, I must say the content here is very vast. So that makes me curious to learn more.
Thank you. Someone else? Well, you can share your own thoughts. Hmm. We'll wait for 1 minute and we'll go ahead with the lectures because we don't want to waste time also. So someone wants to share? Okay, it's fine. So just to give you a basic motivation for today's class. So there's a technique called as ultrasound Doppler imaging. So it's like just would like to know that if all of you know what Doppler is, or just have a basic understanding of how it's like if something's coming close to us or going away from us, how the frequency changes, whether it increases or decreases, how the motion causes the change in frequency. So just would like to know, can unmute yourself and can say, if you know about Doppler, how do we compute the Doppler shift or method? Mm, can someone explain what Doppler is?
Uh, I will go ahead. Uh, we learned about the Doppler shift in determining the direction of blood flow. In a day-to-day example, we took the example of a car with a siren coming towards us, and the difference we observe when the car is approaching us and when it goes past us. In biomedical related, we learn about the ultrasound, which is used. So regarding the Doppler shift, it's I don't recall the exact formula, but it is something related towards the angle of the probe in
Yes.
relation towards the blood vessel, which helps in
Yes.
calculation.
Yes. Nice. Thank you. So I hope everyone got the point that what Make was trying to make over here. So there is something that when we image our blood flow going through a particular vein or vessel or artery, what we see is that the blood flow signal, it's very low frequency signal. The blood, even if the blood moves faster, the rate at which we are acquiring the data, it's very slow because there it appears to be very static. It's not dynamic. So the noise that appears in there might overlap the signal that you are actually trying to capture. So in such cases here, if you see the case, okay, so this kind of case appears that where the detected blood flow, the motion that's going on through the vessel, both of them captures, and hence you're not able to actually differentiate in between the signal and noise over here. So you might also recall there's a property of sampling, which if it's oversampled or if it's undersampled, we say that that happens, aliasing happens. So due to aliasing, we lost most of our signal, and that's why noise comes into play. So we're not actually able to differentiate in between signal and noise. So for that, we actually need to have some kinds of filters, say a low pass filter or a high pass filter, or do sufficient amount of sampling so that we are able to differentiate in between the blood flow as well as the signal that we are getting. Say if the noise is very high frequency signal, so we can just use a low pass filter, extract the signal that we want. And if you have some idea, say if it's a line noise, use a notch filter of 50 hertz. But if you know, okay, there's something, there are more abrupt variations above this particular frequency, use a low pass filter to that cutoff and remove all those frequencies. But before that, ensure that your signal is properly sampled. It's 4 times of the maximum sampling frequency that's given by the Nyquist-Shannon's theorem. So this is how we should know that way to incorporate a particular filter, how to incorporate a filter, what kind of filter frequencies or the cutoff frequency should be decided. So there's a filter. It's like I won't include more jargon over here, but just to give you an overview, it's like what all different kinds of filtering techniques can do. So there's a technique called as singular valvular SVD, singular, I guess it's valve or something, singular vector decomposition, sorry. Hmm. Okay, let it be. Singular vector decomposition. So you know what does this do? Is that, say if you have a signal where this is the microflow that you want to detect from the smallest artery, say the microvessels, whose diameter is approximately around in microns, but why is it going away? Huh. Is it the pointer or so? Okay, so whose vessel diameter is around 100 microns or say 200 microns. But if you go above 600 microns, it's the normal vessels that you have. It's no longer a micro vessel. So you actually want this microflow to be captured. Why the microflow? Just because everything starts from its roots. So micro vessels are something that people are now trying to see the blood flow through it, the anomalies through it, how actually the pathologist changes from direct from the root. So this is the actual blood flow that you will normally get in your arteries or vessels. Now, this blood flow you are well able to reserve. So if you say you use a filter with a cutoff frequency till, yes, say a high pass filter, and you'll just filter out the frequency component from this particular point, you'll get this blood flow. But what about this particular blood flow, which is also incorporating your tissue motion over here? So you need to actually differentiate both of them. So what you do is like you make a matrix which is something like there's some diagonal vector, there's a different vector. Now this three matrix, like the technique of this singular vector decomposition, what it does is it differentiates a particular signal into three matrices, and in a way that it differentiates the blood flow, the microflow, and the tissue motion. So in that particular way, you are actually able to get the microflow differentiated from the blood flow and the tissue motion. So there are different techniques. So this is how filters can actually do and have been helpful nowadays. So we'll start from the basic, that's the optimal filter. So what's an optimal filter is that should be optimal, should be stable, should be, say, adaptive. So more or less that you're able to design a particular filter with the desired characteristics that you want, so that the signal energy is more and the noise energy is less. After all, we all are actually trying to remove the noise, eliminate the noise. So in what sense, that what's a particular metric for that? That's known as RMSE, that is root mean square error. Suppose that you all know that what's root mean square error is just that if you measure something and you have the ideal value for it, then you try to minimize the difference in between these two values. So this optimal filter and this particular fundamentals or this approach is only applicable when the signal and noise both are independent in a way that they are not correlated. So can some of you unmute yourself and say that if I have this signal, say S of n, and noise, say, n of so okay, let's say that signal of S of t and noise of n of t, if both are uncorrelated, what would be the expectation of both of them?
Zero.
Yeah, yes. So in a way that we shouldn't actually get. So when we do autocorrelation or cross correlation, this value will eliminate so that we don't have any n component that is involving the multiplication of both of them. So this actually applies to when the signal is stationary and adds a random process. So last week we saw that, okay, what's a stationary signal, what's a random process, the quasi-stationary and all. So now this is how this is a basic interpretation of how optimal filter is being represented, that if you have an input x of n, it's weighted by n number of weights. That weight is actually varying with respect to the stage that is being processed to. So say w0, w1, w2, and till the n number of stages or delays that you have. So this is something called as tapered delay kind of filter. So this was also in the last session that we saw. So, and then when you sum all of them, you get something that's d tilde of n. Now, this is the signal that you actually, this is the desired one, but this is the ideal one. So what you do is like you find the error and you try to minimize the error in between both of them in a way that what you get is very close to the realistic version that you want. So this d tilde n can be represented as the weighted average of x of n minus k. That's the weighted average of the past as well as present inputs of the x of n. That's the input. And in the end, what do? Is like we find the error, that is d of n minus d tilde of n. Now, can some of you say that why this d of n? I just said that why do we use this? It has
That is
something.
our ideal signal by which we are comparing in order to minimize the error.
Yeah, yes, that's it. Thank you. So next, so one such type of this optimal filter is the Wanel filter. Now, Wanel filter is nothing but a kind of low pass filter that does smoothing to your signal. If you say you have an image and say you take a subkernel in that particular image. So say 3 cross 3, 3 mm cross 3 mm, you took a matrix of 3 cross 3. So you encapsulate the amount of pixels in it and you try moving the matrix all over the, it's like all over your image. Now you see that the matrix is very smooth. There are no high frequency variations. There's no noise. But another such disadvantage for the same is that you'll get, if the amount of smoothing is more, you might also lose the signal. So these are some points that you always need to consider while doing filtering. Number of stages to be considered in filtering, or n number of points, or till which particular point, or what should be the kernel size. And so let's start for that. So there are some notations here before we go into the maths, that x is represented as scalar. These notations are also followed into the references. That's the book, for the first reference book. I don't recall the name, but it starts from an R. So it's bioinstrumentation. So it follows the same notations, hence we'll be using the same notations, and these are also similar to the ones in the lecture slides. And then x bar is like under bar is a vector and 2 under bars is a matrix. So if it's a vector, it's like this is, we have commas over here. I know this is very basic. So it's a row vector and we took a transpose of it. So this is actually a column now that we have. So say m rows cross 1 column, if that's a particular size of it. So here you can actually, and then the input also in the same way. Sorry. Input also in the same way. So how do we define the signal? Is this d tilde of n, that's the multiplication of this input times the weight. It's like the formula that we saw previously, the expected multiplication or weighted average multiplication of x and w. Now we minimize the error, and hence d of n, and this d tilde of n can also be represented as this. Now it's actually, you say, associative or commutative, so you can actually take transpose of either of them and can write it over there. So this is how we can redefine the definition of error over here, with input and the weighted average as like the weights that we have. So how do we define the mean square error? Let's say we have another vector, say that is j of w. So that we can define as expectation of square of this error. So it's pretty obvious from the name, that's mean square error. So it's actually an objective function. And overall, this all terms should be scalar, since error is a scalar value over here. So we input the value, so d of n, w transpose x of n, w of n, x transpose w x of n times w. Now, if you notice over here that something's time variant, something's time invariant. So in a way, what we get is that this expectation, this cancels out. Dx of t, d of n minus 1, x. Okay, so here, this 2 transpose of the signal, this is the desired signal that you have, and this is the individual multiplication of both of them, so the converted transpose of them. So we noticed over here, so what's this particular parameter, this expectation, this is the variance of the desired signal, assuming that it's zero mean. We also saw that why zero mean, because if the mean doesn't give a significance, we'll obviously eliminate the mean and we won't consider it. So within that, we saw that the expectation of x of n cross d of n. So this particular point, this is the, oops, is the cross correlation in between the input x bar n and the desired signal d bar n. So that's an m cross 1 vector. But you can also give it as like represented it by theta. So over here, you might notice that theta is not a function of time. We have not written theta bar of n. Why so? Because the cross correlation won't change with time. It's actually a matrix which will show you where the maximum, and it won't give you the time, it's like time instance or time points for the same. So since both of them are stationary, we'll normally write it as theta n, but if it's not, we write it as this, that is theta n minus k comma n. So this is how, it's like this theta can be represented. So if you might remember, the equation of cross correlation was x of n times of h of n minus k. So you just take the inverse and then multiply both the matrices. So in the same way, we have written it over here. If it's time variant, then we write it in this way. Here it's not, so we have just written it like this. So what you get eventually is the matrix of both of them. Now you might notice that there's something in this matrix here. What's it? The matrix is what? You have something here. and then you have something here. This part and this part. Can see the terms here. This term, this term, this term, this term, and this 0. So we actually knew that, okay, it's not varying with time. It's autocorrelation of the single vector. If you don't have weights of it, then we can represent it as a cross product of the input vector with itself, just multiplying it with itself. But then what the matrix actually tells us. So if you're multiplying the same signal by itself, you'll get the maximum value. That's here. So the diagonal would be phi of 0. But what this matrix actually tells us. Can give a random guess also. That's fine.
It is symmetric, but it has opposite signs, so it must be skew symmetric.
Yeah, yes. So after that, here's how it's like there are different terms for the same. I don't know if I won't zoom it out. I hope it's visible. So the mean square error is again written by, this is how we define the objective function. We saw that there was expectation square, so we gave it as the variance itself. Just writing down the actual terms, that would be easier to remember also. So the weight transpose theta, theta transpose weight, and this. So now this is a quadratic function. If you see, this is term, this is a term, and then you have this two of these over here. So this is actually a scalar because this was our correlation matrix, and this is the variance. So this is a quadratic matrix. So if you differentiate it, you'll actually get a minima or a maxima. But since everything's negative and this is positive value, you'll actually get a global minima for the same. So finding the same, what we do, we take a derivative. So if you take a derivative, you'll see that this variance is a constant, will be 0. Then this is it's like this weight matrix is actually a scalar. So again, it would be 0. So minus this times theta, negative theta. So that's 2 theta, since they are vectors. And then here 2 times of this. So that's would be w square. If you say w square phi, so that would be 2 phi w. That's equal to 0. So this is how you can see that some properties. If you have dw bar of theta transpose w, you'll get a theta bar. Similarly, like this. And so I hope you understand. So the finally what you got from here is that if you take it to the other side and eliminate 2 from both sides, so theta is equals to phi w. So this equation is normally called as Wiener-Hopf equation or the normal equation. Why the normal equation? Because whenever you find the points, they are both 90° to each other, or if you plot it, it would be something like this. You get a minima over here. So the actual angle in between the two vectors or the points is 90°. So if you subtract it from one another, take a dot product, will be 0. So what would be the optimal weight vector for the same? Just take this, and since it was a matrix, you take it to the other side, would be inverse of that, and times theta. So this is not actually, you won't have numericals from this, but some definitions that you might might consider it. It's like, remember, just because eventually when we code it, you'll be able to understand, okay, why we are doing so, why we are taking the way inverse of the same. So then we minimize the same. So how do we minimize it? Now we know that the weight is given as phi inverse of theta. So this would be, here it was sigma square minus this both of the transpose terms plus w transpose phi w. So here you actually difference is like write w naught as phi inverse theta. So eventually you'll get this form. Okay, so Wiener filter. So in a way that we found that, okay, Wiener filter can be represented as weighted average of this terms of past and present. Now you can actually write it as theta k, because theta k was our matrix, cross correlation, autocorrelation matrix. You change it either way, it would be same. And if you remember, there's a property in Fourier transform that if we take convolution, or if we if in time domain we convert two signals in frequency domain, or when taking a Fourier transform, right, we multiply both of them. Vice versa. If in time domain we multiply, Fourier domain we take a convolution. So it's in the same way we can write it as is in a form of convolution relationship. Since when we do correlation or autocorrelation, there's only a difference of sign. Now here this sign is no longer being considered because it's correlation. So it would be the same. So when we now there was this form that you have from the equation, so that if this is the weighted average, this is xx, that's with the signal itself, the autocorrelation, and x with d, that's with the desired signal, that's a cross correlation of it. So if you apply Fourier transform just in the frequency domain, hence represented it by omega, and you take a it's like ratio of both of them. So here these are nothing but the power spectral densities of the input signal as well as the cross spectral densities. What this densities is that you take the Fourier transform of the signal and then square it. If you square it, you get the power spectral density. Cross spectral density, similarly, if you take the power, if you take the Fourier transform of the signal with x with w, multiply both of them, so you get a power spectral density of x comma d, and then take the square of it. Sorry, you get the spectral density, and then take the square of it, you get the power spectral density. Okay. So how do you define the frequency response of the Wiener filter? Is that you just consider that if it's the signal with the signal itself, then if it's given by the desired signal, consider this is a noise, signal plus noise. Always we assume that it's a zero mean noise, but eventually when we do calculations, we need to consider noise in order to know that where the noise signal is actually giving its playing its role into here. And we say that this xd is d itself, just because the input signal with input signal is a signal. So we just assume that, okay, it's d. So it will lead to kind of this signal. So if you say that it's a zero mean signal, then what you eventually get is this would be zero. So this would be 1 by 1. So whatsoever you do, this weight will always be 1. So it will converge its weights in order to be 1. So now you have a flexibility in order to change the desired signal. So the desired signal characteristics can be changed in order you want to minimize the root or mean square error, or you want to take a difference in between both of them, or you want to manipulate your weights in order to form a particular filter, or so that it's like whatsoever your noise is, you can manipulate it in a way. So we saw that adaptive, so what we saw was optimal filtering. So there's something called as adaptive filtering. What adaptive filtering is being used is for interference removal. For example, power line interference. We have major power line interferences nowadays. ECG signal, when we take signal, there's always a noise supply coming through it. Vibromyography, it's like muscle signals. Even muscles is like, not if the electrical connections are giving some problems, but our muscle itself give so noisy output, or the myogram, you're not actually able to interpret it. So what's the optimal problem statement for that? So you need to define an optimal filter in order to remove the non-stationary. Why non-stationary? We'll see. And the interference from a non-stationary signal. So how is it even possible? So you know that, okay, let's see that how is it even possible. First, it should be adaptive, and second, it should be optimal. Okay, so you know that we have this ECG signal. Don't mind my drawing over here. Here. So P, Q, R, S, say T, and this instant is U. So say if you have noise in your signal, all over here noise, and the next signal is started from here. Sorry. P, Q. Like this. Here also. So this is a point where you see that there are no variations over here. We are not actually getting any biophysiological information from here. So you actually coined this point as isoelectrical point. So what you can do is that take this particular segment and interpret the whole signal in the form of this segment. So now you know that if there's something not correlating with the signal, but it actually can be interpreted as noise, then you can remove it. So what you can actually do is that represent the whole signal in terms of that particular segments that you have and reconstruct it accordingly. In a way, you won't actually get the signal that you want, the desired signal, but you will be able to minimize the error from it. So this is how you see. So there's something called as adaptive noise canceller. The same, I've taken the content from the same slides that were there in the lecture slide so that it can be a revision for you too. And it might help you recall the contents too. So here, if the primary input is given by x of n is equals to v of n times m of n, where this is the signal and this is the noise. So you have the reference input from here to which you want to baseline it everything and minimize the error in the form of it. So what we saw that the weights were varying and we were able to compute how the weight would be like the inverse of the matrix times the input value. So here you always have the flexibility to come back and vary your weights, but it's not similar to that of how you have feedback. So it's normally it's a kind of FIR filter over here only. And then you take the sum and give the output over here. So how it can be estimated as that E of n, that's I guess it's cropped. No, it's not cropped. So error can be x of n times this, that is v of n plus m of n. So Sam, you take the mean square error of that is square it. Now this is eventually your signal that consisted of the, so your signal was this, that was v of n plus m of n. Now you took it to the other side, square it, and then similarly, you know that this particular point, or so here, this point, this point, this point, this point, the expectation of both of them would be 0 since they are not correlated, the signal and the noise. So you remove them, what you have left is this particular 2 points. So there are these two optimal, it's like what we saw was the, okay, slide changed. What we saw was the adaptive filtering, in which we saw a few examples. Now, the major goal, if you see, if you don't even recall what all the definitions or the formulas for the same are, you just need to know that what you have to do is to minimize the error. But don't take it in a way that it's like machine learning or signal, it's like say deep learning or so, where you just have to improve your accuracy and it's like decrease your noise, and you use a gradient, it's like any such kind of algorithms, so that you can not noise but the loss function, so you get it less and less. But here it's something that you need to consider what's the signal of interest rate, and with respect to how or what you can take it as noise. So the based on this adaptive filtering, these are the two major or popular methods for adaptive filtering. First is the least mean square adaptive filter and the recursive least square adaptive filter. So I haven't covered the recursive one today because there's too much maths today. You might want to go and then come through it, can have doubts also. Even I myself, if you give me this everything to solve, I won't even able to recall. So it's just that take transpose here and there, see what's not correlated, make it 0, see what's the signal, take the transfer function of it. So you should know all of this. So today we'll just do least mean squares, and next time we'll do this recursive least squares. So if someone might say that what do you get when you hear this least mean squares, we actually computed the mean square error now, but what can be least mean square then? Or if you got an idea of what adaptive filter was, you can just say that now what we did on adaptive filter, we changed the weights, minimized the error, saw how a particular expectation can be found, uncorrelated signals we made it 0, and then we just got the variance of the signals, the weighted matrix, that's it. So in that particular way, what can be least mean squares? Just a guess.
Actually, in this,
Yeah.
actually in this, expectation of the error square is considered to be the error square only.
To be the error square only. Okay, someone else want to try?
In this, weighted coefficients are make somewhat that they relate to the least mean square error of the signal.
Yeah. So it's always the same thing that you have your weights, make the weights in a way that you get the least mean square, it's like, sorry, the mean square error to be lesser and lesser, and you are not actually trying to maximize it, or you see that how you want to manipulate your weights. So it's in filters, everything's about the weights. Okay, so this is a simple schematic for the same. So what you do is that you have an input. This is a simple FIR filter which has no feedback, but we have a flexibility over here that you can just update your weights again and again, again and again in order to minimize the output value. In order to minimize the error, so that what you get is similar to the desired signal. So the least mean square adaptive filtering. So what we do is that now here, instead of taking the total expectation, we take the ceiling value. Oh, sorry, we take the floor of it. That is, we undersample it. We take, it's like we actually say that, in layman, I would like to say that, okay, say that this error is not at all important and we'll give it no importance. And hence, what we do is that we just take the underrated value of it. So you'll get to know that it's like we just treat it as it's not important. Just consider it like that. So for now. So you square the error. So these are the same terms that were there previously. So use the steepest descent algorithm. So if you're not familiar with what the steepest descent algorithm, I'll let you know that what's a gradient descent. That's a basic version of it. So it gives the same value in on. So what you do is that, say if there's a, okay, say it's a kind of, I don't think so. The ink is visible there. Okay, here. It's a kind of image processing, or it came from image processing, but then next to it, people started working it on machine learning and this learning based methods. So what do they do there? Say if you have, so you have loops like this or so, and then your starting point is somewhere from here. Now, what you want to do is that you want to minimize it. Now, it's nowhere near to the region of interest that you're looking into this. So you iterate your algorithm, see and where it goes. So if say the first point went over here, then the next point will go into here, next point will go somewhere else, next point will go somewhere else, in a way that we always try to make it minimum and minimum. So this way it's like this approach works on the slope of these 2 points. So if you have something as x1, something as x2, it always tries to minimize the gradient in between these 2 points so that it achieves the minima over there. So what the steepest descent algorithm also does is that it tries to achieve the minima in a way that your error is lesser, the same thing. So, but here what you see that the weight that you get n plus 1, it doesn't, it's like the future value of n plus the weight depends upon the present value, this mu, that's a weight or the step size which controls the stability and rate of conversion. It actually controls the stability of the system, hence it's placed in between 0 to 1. Why 0? Because you want a condition to play into role, but why 1? So that you can normalize the system itself, because if it's greater than 1, you can't normalize the system. So n times delta of n. So it's always with respect to it's like delta or whatsoever you call this particular symbol, so that you can minimize it. So this is how we represent it, and the least mean square adaptive filtering. So if you go from this point to here, now if you take the differentiation of this whole error equation and resubstitute these values into here, what you get the same equation, but now here there's this what was E of n in between your signal as well as the reference signal. So this equation is also called as Woodrow-Hoff LMS algorithm. There's no such particular meaning to the equation, but what you have to just see that, okay, the weight when varies, or it's not time variant, but the future value of the weights are dependent upon the present values of the weight, and the average or the step size, or you say the weights, should be between 0 to 1, so that it controls the rate of stability as well as the convergence, so that it's always towards the minima. And the here we have the reference value, so that we can try to make it closer to the desired signal, where we know what our baseline was. So this was the most of the gist from it. So what the thing was that it's simplicity and ease of implementation. Why so? Because it's a simple equation. There are no quadratic terms over here. It just depends upon the present value of the input. So now it's stable. When 0 is like the mu is in between 0 to 1, that's no updation of the weight, maximum updation of weight, divided by the largest eigenvalue of the reference input autocorrelation matrix. That's this particular matrix. Hence we have kept this matrix over here so that we can normalize our this signal over here. So divided by the largest eigenvalue. You all know, right, what an eigenvalue is? So it's like we do something in matrices that we take the matrix itself and minus lambda of x, make a characteristic equation, solve for both of them. You get those eigenvalues for, and then for those eigenvalues you solve for the eigenvectors. So it's something like, so you take the eigenvalue, the largest eigenvalue that you get from the reference input matrix, and normalize the whole signal. So in a way, this is the being condition defined so that the filter would be stable, or it won't converge to the minimum. So if the input remain uncorrelated over time, expected value of the tap weight converges to the optimal Wiener solution. Now, if it's uncorrelated, it will again go back to the Wiener solution. So from where we came, it's just simple few advantage or few more modifications of a particular filter. But if you do some tweaks, it becomes the original conventional filter itself. So Wiener is quite popular and also works. So recursive least square filtering we'll see later, like in the next week. So then how do you define a appropriate filter? So last time we saw, not I guess last time or the session before that, that what was the synchronized or ensemble averaging. So can some of you unmute yourself and say, there are these pointers available over here. You can just add up all of them. It's actually the main gist of them. First, you can say what synchronized is, and then you can say what ensemble averaging states. Eventually, both of them are same. I know it was too much maths today, but it's fine. You can take your time. If you want next time, I can also write and solve the maths, but I thought, okay, you all might have went through the lecture slides as just a revision, hence I didn't do and added the slide contents itself. So can someone, apart from the ones who were unmuting yourselves, other ones? Or else I'll say names then. It's like the content is right here. You just have to read it aloud so that you'll also get to learn it, and it's like your memory might be refreshed from it. We can do.
Ensemble averaging is something like you in the last class you have told that we are taking the average of the signal in some definite time intervals like that.
Yeah, yes. And synchronized? Someone else?
That is the second name of ensemble averaging that you also tell in the last class.
Okay. So there was one thing for synchronized, that if you want both of your, it's like whatever two instruments that you're working with, or one from one if you're sending a signal, and from one if you're acquiring a signal, the receiver side, you want both of them to be synchronized for, so that you start actually from t equals to 0, so that you have a particular timeline or from where you start and the particular definite duration of time. So here it's not actually the entire duration, but it's also from t equals to 0 to the time of acquisition. So there are these things that for that the signals should be stationary, quasi-periodic, or cyclostationary, that should be periodic. There should be multiple realization for the same, that we called as ensemble averaging. A time marker should be there in order to align or make different copies of the signal. And obviously that the noise should be uncorrelated with the signal, and it can be a zero mean stationary random process, so that it's always a zero mean and we don't get more variations of noise within our signal of interest. So next is the temporal moving average filter. So what is the name itself here? Shubham? Okay. Pradeep? Siddhi? See, guys, even if you read from the slides, it's very fine with me, but I should know that if you're getting it or not, because it's actually written it there, and you just have to read it aloud so that you get to know it and you are aware of it. I know that you all know all these contents and all, but just so that I also know that you know, it's just for that. I'm no one to judge you over here. Just so that I'm trying to convey something. So can unmute yourself and speak. And there are less slides available. Then we have our 10 assignment questions. That's it. We're done. Okay. Ayush,
Yes, ma'am.
what day is like? Do you recall what temporal moving average was?
Yes, ma'am. In this, ma'am, signal stationary random process, at least over the duration of moving window.
Yeah, that is fine. But what was moving average? So
Moving average,
you
ma'am, like when we are averaging the signal, so our window is of variable size. We can vary it according to अपनी सहमति से, like this.
no. So if you have a particular signal and say if it's any kind of signal, say it's a square. And then here I want to take a moving average of this particular signal. But what I have decided is that I'll take a time window of 0 to 2 seconds. So what I'll do is like if this is 0, this is 2, 4, 6, 8, 10 or so. So what I'll do is like, okay, it's not actually representing a time scale, just randomly. So what we do is like we take a signal of this particular frequency, take it, save it, take it, save it, take it, save it, and take the average of all of them. So this is how we move across the time period. Now here it's same. What if it's like this over here? What if it's like this over here? So this is how you take a moving average filter. So here also the same thing is that noise should be uncorrelated. Now this too, now you can't actually say that, okay, if this is the signal and this is the noise, but it's actually a signal that's represented over here. But it can be a noise if there's something like this. So you never know. So if this, it has a maximum power, hence the process that why do we do autocorrelation always first and then cross correlation, so that we don't misinterpret noise instead of the signal. So the signal is relatively low phenomena, and then fast on time real time filtering is possible over here. So if you all might have seen oscilloscopes, what we do over there is there's a um, menu of like, okay, so there's a particular window where we have something written as acquire. So with that acquire, when you see that, if it will show you that, okay, if the signal can be acquired in a sample mode, in average mode, or if you're acquiring in average mode, how many realizations of it do you want? If you increase the n number of realization, it's ensemble averaging. But if you it's like the number of averaging is same, but if you increase the time duration of it, it's the temporal moving averaging filter, because the reference or the timeline is always the same over there. So then we have frequency domain mix filtering. So here what do we have is that the signal is again, so in frequency domain, we do the averaging. Oh, sorry. So it's not about averaging over here. It's about filtering. So what do we do over here is that convert the signal, the time domain signal into frequency domain. And then later we like do the filtering over there, because what people prefer is that time domain, it's always nice, but in frequency domain you actually have an information of the spectra of the signal, the magnitude of it, as well as the phase of it. So from the phase, you always can exploit many of the things from it, say the strength of the signal, how it's varying with respect to time. Magnitude will not always give you everything, but phase always says about the major it's like characteristics of a particular signal that you're trying to see. So for that also you want a stationary random process. Noise also same. If the signal should be limited in bandwidth or the noise should be limited, so that you know that okay, which one has a particular f0 and f1, so I'll be able to filter it nicely and well. So keep in mind everything is very ideal over here. It's not how you will, it's like when you go out of your bachelor's degree or in your final year of degree, you do some projects, you do thesis project or reports or so. You won't actually, if you're trying to acquire something and then you're doing some data processing on it, you won't actually get this clean signal. Even if you're trying to connect a, you might have seen if you try to connect the Arduino with LCD, you always don't get proper connections of it at the very first. You always need to debug it somehow here and there. At least I didn't get when I was doing. So just saying. So it's always that you should know a random frequency bandwidth for the same, so that you have an idea that where you actually want to filter it. So loss of information in spectral band that can be removed from the filter, it won't seriously affect the signal itself. Again here, online and real-time filtering is not required, even if it's in the spectral domain, because if it's online or real-time, you'll actually do the filtering in time domain. So that's not always preferable, because frequency domain filtering is what people prefer, so that you get the information about the signal more. So similarly for Wiener and adaptive filter, this all stationary, limited, should be optimal, the information loss should be less, everything follows. So previous year assignments, 10 questions. We actually completed it fastly today. That's so within an hour. So do you have any questions? Or if you have any questions and won't like to say now, you can also stay back and I'll be happy to help you. So as we did in last time, that I'll show you the question, try to answer it. For the recursive least square, there are 2 questions, we'll skip them. Next time we'll do those questions after learning how their maths and how the transforms go by. If you have seen in the lecture slides, is very well, it's nice. If you are able to answer, you can try so. If not, it's perfectly fine with me. So any questions till now? Do you want me to go through the previous slides, or you'll stay back and tell me? Anything works. If you have any questions, can raise your hands or can unmute yourselves and speak, or I'll go through the assignment. I guess not. So we'll go through the assignments then. Okay. Which of the following is an optimal FIR filter? Wiener filter, A, B, C, D.
Wiener filter.
Okay. So can you tell why so? We didn't see least, it's like recursive least square, but we saw least mean square filter. What was the difference in between both of them, and what made least mean square filter same as Wiener filter? It's like not actually you, someone else can also answer. That's fine. It was there in the slide. Come on, come on. It will only help you to recall things.
Because optimal is for stationary, and option B and C, which are for adaptive filtering, they are for non-stationary.
That also works, but we saw something else. What actually is an FIR filter? That's a finite impulse response. It doesn't have a feedback. But we had something in this 2 least squares filter where we had something, we changed it again and again. That was not there in Wiener filter. Hence, it was very simpler.
Ma'am, step size and forgetting factor.
Sorry, what?
Ma'am, step size and forgetting factor alpha.
We didn't actually see that forgetting factor. It's in the RLS, but yes, the step size one, how you change the mu in order the system is stable so that the weight always converges. And here in LMS, the weight is adaptively changing and changing, whereas in Wiener filter, it's a simple equation and it doesn't change. 2 seconds. Huh? Sorry, I had something to deal with it. Okay, so which of the following is not true? A, B, C, D. Wiener filter gain is inversely related to the noise power spectral density. It's directly related to it, or it's inversely related to the signal power spectral density. We saw the formula where we took the inverse and took the Fourier transform, and then we had something 1 by 1 plus something by something. Guess is also fine. It's just ABCD.
I think C option.
Someone else? I also don't know the answer. When I flip it, I'll know. But someone else? C is fine.
Yes, ma'am. Looking like C option only.
Okay, let's see. So can you say what was the formula for it? It's like not only you, someone else can also unmute. 1 by 1 plus?
SM
What
by
is
SD.
that?
SM of omega upon SD of omega.
Yeah, yes. So SM was?
PSG
Noise?
of the noise.
Yeah, and this is of the desired signal. This is from the RLS. We'll see it later. It's fine. Okay. Adaptive filtering is applicable if
B.
non-stationary and uncorrelated with the signal. Yes. Least mean square filter is stable when? I guess it's pretty much C.
A.
A.
Yeah. The weight update in LMS adaptive filtering depends on?
Present error.
Present error. What was the formula? It was W of n plus 1.
Equal to
With,
Wn plus 2 mu E of n into R of n.
yeah, yes. Okay. Oops. Okay, this is from RLS. It's fine. ABCD lemma is, oh, it's also of that. So carry along all of this. Okay. Which of the following filtering can only be applicable if multiple realizations or copies of the signal of interest are available? This is within the question.
B. Synchronized averaging.
Yes. In the Wiener filter, the error function depends on the
past and present.
D. Okay, that's done. Thank you. If you have any questions, you can stay back and let me know. Or else we are done for the day.
Ma'am, I have a doubt.
Hi, yes.
Ma'am, there is a question in the assignment, question number 8. Which of the following filters do not have frequency domain interpretation?
Okay, wait.
So,
This year's assignment, right? Current assignment.
yes, ma'am. Yes, ma'am.
Okay. Question number 8. Okay.
Yes, ma'am.
Hi, yes.
So,
Do not have a
what is the
frequency.
answer? Like Wiener
Yes.
filter have,
Huh.
and the other three filters, LMS, synchronized, moving average.
So LMS also has.
Okay.
We saw. So within synchronized averaging and moving average filter. So you might want to see the week 2 lectures perhaps. There we saw for one we had, for other we didn't have. It's like explain you, but can't actually tell you the answer because there's some external over here. Hey, catch me.
Ma'am, can you tell me again, synchronized and moving average, in two of these we have this do not have frequency domain interpretation, right?
Mostly they don't, but last time also when we saw, we actually didn't see differences like the frequency response of them. But wait, I'll check again. Because it's normally done in time domain, so either the answer would be both of them, or oh yes, one of them has, because it's FIR filter. One of them has one, the other one doesn't. So if you just Google it, you'll get the answer.
Means one of them is FIR filter and another is not, like that?
No. Yeah, yes.
Okay.
Because if it's an, it would have a frequency domain interpretation. If it's not, it's just a time domain realization.
Okay. Okay, ma'am. And in the assignment, Vani, that you have given the previous year question only that we have done today. The error in the Wiener filter depends on both present and past values of the input, no?
The present and
Ye-
past samples input.
Okay, ma'am.
Yeah.
This question is it. In the today's assignment, there is a question that what is the optimal FIR filter? Like it's first or second question only.
Wiener filter, right?
Is an optimal FIR filter. I just have a doubt why Wiener filter is an optimal FIR filter and why these recursive and least mean square filter is not.
That's the same thing was there. So here, if you just like consider it as simply that in Wiener filter, the weight equation is very simply given. Whereas in these two, the weight equation can be changed again and again. So it's something that you manipulate in order to get the error function approximately 0 or very minimum. So that here you have a flexibility to change it, but here you don't have. That's it.
So I think if I have the flexibility, then it must be optimal. Huh?
Hi, if you have the flex, so that what we saw previously, that if you change the weight or that particular mu value or something was there, if you change it in a way that the wait, I'll go through the slides. It was there. Yeah, here. If the input remain uncorrelated over time, then the expected value of the stack weight converges to the optimal Wiener solution. So what I said, that this particular filters are just modifications of the Wiener filter, but eventually what is traditional and conventional or what people follow nowadays also is the Wiener filter. So these are just modifications, like a tidbit modification, which are only applicable at some points of time, but not in general.
Okay. Okay, ma'am. That's all.
Thank you.
Like they are also adaptive filters. So in adaptive filtering techniques, there is a reference signal also. Like um, that reference signal is correlated to noise and but not correlated to the to our desired signal.
Yes, signal.
So that's
Yes.
so that's why also they are not too much optimal.
Yeah, yes. So because when you see is like if you have a particular signal, say you are acquiring ECG of something, but you're not actually acquiring ECG. So there is also some points from where it's like we have different kinds of electrode for the same. So say if you are acquiring ECG from using the precordial electrodes, that's the chest electrodes we have, and then now you know that what's the baseline for it. Also, you know what can be the supply noise because ECG is like just connect all the electrodes. What is the preferable noise that you will have is the supply noise. So you know the baseline, you know the reference as well as you know the supply noise. So now you're able to differentiate the noise from the baseline and the baseline from the signal. So because we actually have those R peaks and all those over there. So in a way, the reference value helps us to differentiate or isolate the signal of interest.
Okay, ma'am. Okay, ma'am. That's all. Thank you very much.
Thank you. Hmm.
Ma'am, I have a question. Actually, it
Yes.
is non-specific. I just want to ask, like, while referring to the lectures, the maths which is done, to catch up to it, it feels like an uphill task. Eventually, it happened.
Yeah.
And beyond that, in the assignment, the questions that we have, we make
Mhm.
interpretations from that maths that like the error about the error and the inputs which might be present or past. So I wanted to ask that it's is it like will it like the habit of making these interpretations, will it happen over time, or there is like prerequisite maths that we need to understand?
So, what's your background again?
I am a third year biomedical engineering student.
Okay, so you might have learned basic signal processing till now, some ADC, analog and digital circuits.
Yes, ma'am.
Okay, so it's totally fine. You have learned this FIR, IR filters, Z transform.
Yes, ma'am. Yes.
So it's totally fine. So as in when you go through this, so this stages and everything was also new to me when I learned all of this. It's a eventual process, I might say, but then again, keep a habit of looking at the circuits, but not at the equations. So looking more at the circuits will give you an idea that, okay, how it's varying. It will also make you easy to write the equations. Whereas some equations are there very tough. There's like not tough, but you can't actually remember all of these equations. It's just that you need to know the logic behind it. If you know the logic, it's very easy for you to solve, even if it's a big question given to you. So it's fine. It's an eventual process, I would like to say. But again, you just need to know the logic. That's the only thing. Because in signal processing, it's not the steps that you write or it's not the process how you do and all. It's just that you should know that, okay, what's happening within the system, how the signal is being propagated or what all transforms are being getting into it, and then you'll be able to solve it. It's very fine. It's very usual. It happens.
Thank you, ma'am. I just would like to add a small question to that. So if I take the example of, let's say, lecture 16, and in that there's a concept of ABCD lemma. So that it was a long mathematics up to 13 equations, and
Yes.
I was able to follow the maths. But let's say if a professor he was able to assume new variables in between, like P of n, or let's say K of n. So we are able to follow that part, but is it an expectation that at a certain point we ourselves are able to switch those variables?
It's perfectly fine, because what we do is, like, if you go through the book, you'll eventually just like make yourself very adaptive to that particular thing that's written over there. So even Professor Sudapta he's teaching a course for this while, so he's like, okay, we'll use this variable. This would be the thing. Now, if you just take x of n as the input signal and n of n as the noise signal, it's totally fine. You just need to know that where the particular variation is being coming, or why you're calling this particular signal to be S, like say RLS, or what's a variation from LLS. That's it. So if you're able to follow along, it's it's like finely well. But if you're not being able to follow along, see it once or twice. If not, just solve it again by your own.
All right. Thank you, ma'am. Thank you.
Thank you. Okay, if it's okay, thank you. And on